Good morning. Hello. Good morning, everybody.
Good morning, sir.
Welcome to this morning session. Of course, you are all very much familiar with the previous cycle, that is the yesterday cycle, that is the Carnot cycle and Otto cycle. In that Carnot cycle, you are already familiar with the thermal efficiency and then heat supplied, heat rejected, work done, and then the mean effective pressure. Mean effective pressure. In the diesel cycle, I would like to highlight this previous Otto cycle. Comparison to this diesel cycle, Otto cycle is applied to the spark ignition engines, as you all know that. Instead of the spark ignition engine, there is one more category of engine, that is the compression ignition engine or diesel engine, it is called as. The diesel cycle consists of two isentropic, it is also called reversible adiabatic, one constant pressure or isobaric, and one constant volume, it is also called as isochoric. As you all know that this is you are studied in the basic thermodynamics. In that you might have heard that the isobaric and isochoric. Isobaric is nothing but the constant pressure. Isochoric is nothing but the constant volume process. The cycle was first proposed by the Rudolf Diesel in 1890s. The diesel cycle is the ideal cycle for the compression ignition engines. I said this in the earlier also. The compression ignition engines, usually the diesel cycle is referred. To calculate the thermal efficiency of this diesel cycle, as like that the Otto cycle, diesel cycle also will be having two diagrams, that is the pressure versus volume diagram, temperature versus entropy diagram. Here the pressure versus volume diagram and temperature versus entropy diagram, diagrams will be having its own advantage and disadvantage, so that we have to refer both the diagrams whenever we require. Okay, whenever we require. See, as I said, two reversible adiabatic or isentropic process. Isentropic, how do you find this pressure and volume diagram, whether it is isentropic or not? Here only the entities or the pressure and volume will be seen in this diagram. But if you come to the temperature versus entropy diagram, here you can observe the 1 to 2, the state 1 and state 2, the entropy. If you come to the x-axis or the abscissa, if you come to this, the state 1 and state 2, the entropy S is same. If you extend this line, the both states will be falling on the same point. That's why it is called as isentropic, or constant. Entropy is constant at both the states. But here in the PV diagram, we can't able to see this. Only we can observe the changes of pressure and volume, but entropy, the changes we can't observe here. But in this diagram, we can easily sense whatever the changes in the entropy or the reversible adiabatic process can be observed here. Here, I'll come to all the assumptions. Whatever the assumptions we are assumed for the year standard cycles, all are holds good. The cycle is a closed one. The working fluid is the ideal fluid. The means air. The heat is supplied externally to the engine. Means here heat supply, heat rejection is there now. we are not going to supply, suppose the any particular fuel. Diesel cycle means we are not supplying the diesel, but only the thing is after burning the unit quantity of diesel, the whatever the heat is liberated, that heat will be the sent to this the cycle engine, so that the after the running the engine, this cycle will be framed. Okay, like that the diesel engine working. Second assumption is we are supplying the equal quantity of heat to the engine cylinder. Means the equal quantity means unit quantity of diesel means 1 kg of diesel, 1 liter of diesel we are burning, and then whatever the amount of heat is liberated, the same amount of heat is passed to the engine cylinder, so that the instead of burning the diesel, we are supplying the equal quantity of heat. And then the specific heat of the working fluid. Working fluid is the ideal fluid, that is the air. The working fluid of air, the specific heats are same. There is no change in the specific heats, and also no change in the kinetic energy and potential energy. Like that, whatever the assumptions we are assumed all are what's good in this cycle also. In this cycle means diesel cycle also, or it is called as constant pressure cycle. This is also called as constant pressure cycle. Why it is called as constant pressure cycle? The whatever the heat we are supplying into the engine cylinder is the constant pressure heat supply takes place. Equal quantity of heat. We are not burning the diesel in this cylinder, engine cylinder, but equal quantity of heat is supplied to the engine cylinder at a constant volume. You see here, state 2, state 3. If you extend on the abscissa ordinate, their y-axis, their both the states are falling on the same point. That's why it is called as constant pressure process. Okay. Again, 3 to 4. I'll come to the 3 to 4. Adiabatic process. Or it is called as isentropic process. Isentropic means the at state 3 and 4 both are will be having same S. Yes, if you extend this the 3 and 4 state to this x-axis, the both state 3 and state 4 are falling on the same point. That's called as the isentropic or reversible adiabatic. In other words, it's called as. I'll come to the working of the diesel cycle. I've already explained on the diagram, but in words also it is there. I'll explain once again. You be careful while observing this. Diesel cycle is plotted on the TS, the PV and TS diagram as shown in the above diagram. Isentropic or reversible compression 1 to 2. That during the process, air from the initial state is compressed isentropically, pressure P2 and the temperature T2, volume decreased from V1 to V2. The P1, it is compressed to the P2. The pressure P1 is here and P2 is here. The pressure increases, volume V1, you see here. You see here. V1 and V2. The initially volume is V1 and V2. Then one more thing yes discussed here, temperature. The temperature T2, because due to the compression, anything if you compress the gaseous thing, due to the bombardment of the molecules, there may be the changes of temperature. There may be the changes. It changes very slightly. That's also counted. The here T1 becomes T2, this bombardment of the molecules. Okay, like this cycle repeats. Okay, 2 to 3. Isobaric or reversible constant pressure heat supply. Reversible constant heat supply 2 to 3. Reversible means it can be reversed from 3 to 4, 3 to 2, 2 to 3. Means it is a closed cycle. That's why it is called as a reversible. Totally reversible cycle we are used here, so that it is called as a reversible process. And then 2 to 3, isobaric or the reversible constant pressure heat supply. 3 to 4 is the isentropic reversible adiabatic expansion. Here you can observe the 3, state 3, it is a pressure P3, and P4, it's a pressure P4. Pressure decreases. V3 is here, V4 is here. The volume decreases. Volume increases. Pressure decreases. Volume increases. That's why it is called as a expansion process. Here at point 3, supply of heat is cut off. Point 3, it is cut off. This is very important. Cutoff ratio we are defining here. Cutoff ratio. Pressure 3, cutoff takes place. Up to the heat supply starts from point 2 or the state 2 and the stops at 3. Cutoff means the stopping the heat supply takes place at 3. Okay, and air is allowed to expand during the work. The pressure and temperature decreases P4 to T4 respectively. Volume increases V4, as I explained. Isochoric or reversible constant volume heat rejection. You see, one more important thing here. Heat supply takes place in constant pressure. Heat rejection takes place in constant volume. You can observe here. It is horizontal line, it is vertical line. Vertical means if you project this line, the state 4 or state 1 up to the x-axis means the abscissa, right? It is falling on the same state, same point. That's why it is a constant volume process. Heat rejection takes place 2, 4 to 1, suffix 4 to 1, 4 to 1. Okay, heat rejection. Heat rejection from the air to the external sink, thus bring the pressure and temperature of the air to the initial state. That completes the diesel cycle. After that, we have to analyze. We have to analyze the diesel cycle. Referring the PV and TS diagram, as shown in the above diagram, heat supply. Heat supply is Q2 to 3. Is, as we know that MCP delta T. Heat means MCP delta T. Some cases MCV. The M is the mass of the ideal fluid, that is the air. Cp is the specific heat of the air. T3 is the air temperature minus T2. Come here. MCP. Why we are using Cp here? Cp is constant pressure. Heat supply at constant pressure because it is a constant pressure process. Okay. M is the mass. Cp is the specific heat of the air. That is the standard value 1.005 kilojoules per kg Kelvin we have to take. We have to remember at the time of examination, he may mention in the question paper or may not be mentioned in the question paper. But one thing for the air means that is a standard value, that is Cp value 1.005 kilojoules per kg Kelvin we have to take. Here in the heat rejection process, it is takes place in the constant volume. It is heat supply in constant pressure. Its heat rejection takes place in constant volume. So that here MCV delta T we have to take mass of the ideal gas into Cv is specific heat at constant volume, that is 0.718 kilojoules per kg Kelvin for air, standard air. We have to take that. Again, once again, I will highlight you here. One thing you should remember, the Cv value of the air is the standard value. You should remember this. In the examination, you may give or may not give in the examination because it's in the derivation you are using only Cv value. But in the problem, also you have to calculate the heat supply and heat rejection. Heat supply and heat rejection. Here, M supply Q2 to 3 MCP T minus T2. If you have any one book, you just open the diesel diagram, diesel cycle diagrams, then you will come to know. Same type of diagram will be there in all the books, but only the notations may be changes, but diagram is same. Heat rejection, Q rejection, Q4 to 1, MCV, T4 minus T1. Here, T4 minus T1. MCV is, it is the constant volume because it is vertically there. Okay. Thermal efficiency, as you all know that for any day, any cycle, air standard cycle, thermal efficiency is equal to neta is equal to 1 minus Q rejection minus Q supply. If you substitute both the equations here and then you take out the MCPs and CV, mass will get cancelled. CV by CP, we don't have any ratio. If you bring this CV to the denominator, it becomes CP by CV. CP by CV is the gamma of the air. Gamma of the air is the standard value 1.4. You should remember this also. For the problem's sake, you should remember this also. Okay? Gamma is equal to Cp by Cv. That is the 1.005 divided by 0.718. It becomes a 1.4. If you simplify this, 1 minus 1 by gamma is there, gamma. From the numerator, you take out the T1 outside, T4 by T1 minus T1 minus 1 divided by, you take the denominator T2 outside, T3 by T2 minus 1. This equation, you take it as equation 3. Let us define the volume ratios. Compression ratio is RC, it is RC. V1 by V2 means the state here. Compression ratio is V1 by V2. V1 by V2. Compression ratio takes place between the compression process only. And then expansion ratio. This is expansion ratio is R suffix E. This is, don't confuse this. R suffix E, expansion. Expansion takes place between the 3 to 4, so that the 4 is the higher volume. That's why V4 by V3. You see that. V4 is this much is the volume. V3 is small volume. V4 by V3. Expansion takes place. After that, one more ratio is cutoff ratio. It is occurs only in the constant pressure process. It is V3 by V2. That is the volume V3 is higher one. The V3 is the lower one. Cutoff ratio. V3 by V2 is the cutoff ratio. By looking into the diagram, we can explain the different ratios. How many ratios are comes into picture here in this derivation? One is the compression ratio, occurs only in the compression process. That is the 1 to 2. It is the RC, the denoted by R suffix C is the compression. Here the V1 by V2. V1 is the higher one divided by lower volume. Here cutoff ratio rho, it is denoted by rho. It is the higher volume is V3 by V2. It is expansion ratio occurs in the expansion process, that is 3 to 4. Again expansion ratio R suffix E. E is the expansion. The lowercase letter E. R is the ratio. It becomes a higher volume divided by volume is V4 by V3. I'll come to the derivation. Here RC is equal to RE expansion ratio. Expansion ratio into rho. Rho is cutoff ratio. If you multiply this, both the two, you'll get the RC is equal to RE into rho. Recalling that once again the reversible adiabatic compression or isentropic process 1 to 2. 2 by T2 by T1 is equal to V1 by V2 raised to the power of gamma minus 1. V1 by V2 is nothing but the compression ratio RC raised to the power of gamma minus 1. Here. Okay. 2 to 3 is the isobaric or constant volume, constant pressure process. V2 by T2 is equal to V3 by V2. It implies that T3 by T2 is equal to V3 by V2. It is nothing but the rho. V3 by V2 is nothing but the rho. It implies that T3 by T2 is equal to rho. 3 to 4 is isentropic or reversible adiabatic. T4 by T3 is equal to V4 by V3. That is again divided and multiplied by the V2. Okay. Here V3 by V2 divided by V4 is equal to V1 because constant volume process. Note ko bekilling. ನೋಡ್ರಿ V4 is equal to V1. Correct? That's why V4 is equal to V1 ಇರೋದ್ರಿಂದ ಇಲ್ಲಿ directly you are substituting the instead of V4 you are substituting V1. Divide and multiply by V2. It becomes the V3 by V2 is rho, V1 by V2 is RC raised to the power of gamma minus 1. T4 is equal to T3. T3 ಗೆ ಏನು ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡ್ತೀರಿ? T3. Reverse substitution. For T3, it becomes a T2 into rho. For T2, T1 into RC raised to the power of gamma minus 1. Here T2 you are substituting here from the T2 is T1 into, if you bring to this side, T1 into RC to the power of gamma minus 1. You substitute T2 here. T3 is equal to T2 is T1 RC to the power of gamma minus 1 into rho. Okay, same thing we are substituting here. T3 is equal to T4 by T3 into RC to the power of gamma minus 1 rho. Here rho into rho divided by RC raised to the power of gamma minus 1. It implies that T4 by T1 is equal to rho to the power of gamma. Okay, T4 by T1 is equal to, if you bring to this side, both these two things will cancels. RC to the gamma minus 1. You split this numerator rho to the power of gamma minus 1, RC to the power of gamma minus 1. This thing cancels. If you take this side, then it becomes the rho to the power of gamma minus 1 plus 1 minus 1 get cancels. Only gamma will be remaining. The T4 by T3 is equal to rho to the power of gamma minus 1. Diesel, if you go to this T4 by T3, T4 is equal to, just you are calculated, T4 by T1 is equal to raised to the rho to the power of gamma, T4 by T1. T3 by T2 is nothing but the, you see here, T3 by T2 is nothing but this thing. Substitute all the things, you'll get the thermal efficiency of diesel cycle. You'll get the 1 minus the rho to the power of gamma minus 1 into gamma into RC to the power of gamma minus 1 into rho minus 1. Okay? Or else you can take this to the outside, and then if you multiply the gamma to the inside, this denominator bracket, you will get this as the 1 minus rho to the power of gamma minus 1 divided by RC to the power of gamma minus 1 into rho rho minus 1. This completes the thermal efficiency of the diesel cycle. Here, I'll recap this. Diesel cycle, what the ratios are important. 3 ratios are coming. One is compression ratio, cutoff ratio, expansion ratio. After that, the CP and CV values, gamma, like that, the constant heat supply, CP, CV, all those things you should be very clear. Mean effective pressure is nothing but the total pressure which is applying on the piston of the any one engine is called as a mean effective pressure. Here in the diesel engine, the work done by swept volume. In the previous class I shown the work done by swept volume is the V1 by V2, the volume subtended by the piston between the 1 and 2, V1 and V2. Okay, V1 and V2. That is V1 minus V2. The Q net is heat supply minus heat rejection. V1 if you take outside, 1 minus V2 by V1. This is nothing but the 1 by RC. Here again, once again I have written all the equations. Heat supply 2 to 3. It is a constant pressure. That's why CP value I have taken MCP T3 minus T2. Rejection is MCV T4 minus T1. V1 is equal to MR T1 by P1. And V2 by V1 is equal to 1 by RC. Substitute all the things, you'll get the answer. Okay. Substitute all the things and simplify the things. Simplification I won't tell you. Again, in the auto cycle, I have already explained. That is a simple mathematics. You should go through the simple simplification process. Okay, after substitution, as a simplification is very easy. Only the thing is that at the time of doing the class, the simplification is very, very easy. You are telling yes, yes, sir, simplification is very easy. But at the time of doing in the examination, you are feeling very difficulty, so that you work it out once or twice or four times, five times, six times. N number of times you must write it, these derivations. If you know the derivations, then only you are in a position to solve the problems, because the both the derivations and problems are inculcated. Means they are, if you know the derivation perfectly, then only you are in a position to solve the problems very easily. Otherwise, it is not possible to solve the problem. Okay, it feels, you may feel very difficulty. You may not get the formulas properly at the time of solving the problems. So that my sincere advice is, you must be in a position to the right calculations without seeing any notation, without seeing the any book or notes. Then you are feeling very easy at the time of solving the problem. Okay. Here in this subject, stepwise marks will be given, so that for PV diagram you may allot the 2 marks, and then up to this thermal efficiency, the work done by heat supply, the up to 40-50 marks will be allotted, 50% mark will be allotted, and then remaining the last step simplification, you may allot up to 80%. If you write the whole steps and then final answer also, he may give the 100% marks also. He has to give, he will give. Okay, like this, the scheme of evaluation is there in this applied thermodynamics is concerned. Let us see the one problem after derivation. One problem. I'll read this problem. Compression ratio for air standard diesel cycle is 60. Compression ratio is R suffix C. That is nothing but the V1 by V2. Volume of initial volume minus initial volume divided by final volume of in the compression ratio. The temperature pressure at the beginning of the isentropic compression process. Beginning of the isentropic compression process is this one. The here temperature is 15 degrees Celsius is given. Pressure is given 0.1 MPa. How to convert this megapascal? Mega means 10 to the power of 6. If you want to convert this into kilopascal, means it becomes the 10 to the power of 3 into 10 to the power of 3. 1000 into 0.1 means how much it becomes? You multiply this mega with 1000, it becomes a kPa. Okay, 1000 mega means 10 to the power of 6. 10 to the power of 6 is divided into 10 to the power of 3, 10 to the power of 3. It becomes the
100 kilopascal.
100 kilopascal. Okay, thank you. 100 kilopascal. Okay, like this. Here in the problem, I am stressing here conversion of this pressure is very important. If you won't convert this, the whole problem will be going to wrong. Okay, this is very important in the problems. During the constant pressure process, heat is added until the temperature reaches to the 1480 degrees Celsius. During the constant pressure process, heat added until the temperature reaches, means temperature T3. T3 is higher one, right? 1480 degrees Celsius. Determine the cutoff ratio, rho, heat supplied, QS, the cycle efficiency, neta, TH, and mean effective pressure, right? You see, for the diesel cycle, he has given data. RC is V1 by V2 is 16. There is no unit for the ratios. And then temperature T1 is a 15 degree. It is becomes the absolute Kelvin, 288 Kelvin. T1 is the 0.1 into 10 to the power of 6 Newton per meter square. And then T3 is 1753 Kelvin. For assumption, sometimes he may give, he may not give. So that you must be in a position to remember all these four. These are very, very, very important. For ATD, you must remember this. You must remember this. Cp value 1.005 kilojoules per kg Kelvin or 10 to the power of 3 joule per kg Kelvin, and Cv value again same 0.718 as I said. R value universal gas constant, it is a 0.287 kilojoules per kg Kelvin is equal to 0.28 into 10 to the power of 3 joules per kg Kelvin. Gamma, if you divide the Cp by Cv, you will get the gamma 1.4. To calculate the cutoff ratio, V3 by V2. Cutoff ratio takes place in between 3 and 2. The cutoff takes place up to 3. V3 by V2. Heat supplied Q2 to 3. Heat supplied is Q2 to 3. M Cp delta T. T is T3 minus T2. And cycle efficiency and mean effective pressure. All these things you must find. Okay. Solution, isentropic process T2 by T1 is equal to V1 by V2 RC. Here you can calculate the T1 is 288 into 16 into 1.4 minus 1. You can calculate this. And for constant pressure process, cutoff ratio rho is V3 by V2 is equal to T3 by T2. It is 1785 is T2 you are calculated 873 Kelvin. If you substitute this, you'll get the cutoff ratio. Heat supplied Q2 to 3, Cp into T3 minus T2, 1.005, it is a standard value into 10 to the power of 3 into the T3 is given and T2 you are calculated, you are substituted Q2 to 3 joules per kg. Isentropic expansion, here the 3 to 4, T4 by T3 is equal to rho by RC. T4 is equal to T3 rho into RC. This derivation I did in the diesel cycle, you refer that. T3 into rho by RC, right to the power of gamma minus 1. If you substitute all the things, you'll get the heat rejected T4 by T4 minus T1. Here the Q4 to 1 is 342.17 kilo into 10 to the power of 3 joules per. Cycle efficiency is 61.613, it is 61.31. At state 1, the P1 V1 is equal to RT1, V1 is equal to RT1 V1, you'll get the V1. Mean effective pressure is W net divided by V1, Vs, this is because this is Vs, Q2 to 3 minus Q4 to 1 divided by V1 minus V2. Here V1 if you take out 1 by, it becomes V2 by V1, it becomes 1 by RC. Q2 to 3 minus Q4 to 1, you substitute all the things, you will get mean effective pressure. That's all, mean effective pressure. Okay.